All right, so now we are going to kind of diverge a little bit, but we're going to kind of stay on track. The book talks about this thing called the dispersion relationship. This is something that we constantly see throughout quantum field theory. And it's this idea that we've seen it in the Klein-Gordon equation. We've seen it in the Dirac equation. We've seen it in the Proca equation and their solutions. And what it is, essentially, is this idea right here. M squared. Because when we take M to both sides, we get something that looks an awful lot like an operator that we've seen countless times already. This showed up in the Klein-Gordon equation. It showed up when we did this, if you recall, for the Dirac equation. When we treat this as an operator, we found this to be equivalent to this. And then we found out that d sigma a rho minus m squared a rho equal to 0. This is very interesting, and what we can see here is that a rho obviously is going to have this this structure to it where it's proportional to e to the I k mu x mu, like this. And we've seen this already. We've seen this countless times where we're able to put this into here and find that it's a solution. This is, what is this again? This is oscillatory behavior. Right? And then if we want to take into consideration all the components, a rho is equal to e rho e to the I. There should be minus. It doesn't really have to be minus, but just for convention's sake, this is what this looks like. And actually, this is supposed to be mu. So we have something that's taken into consideration all of our components, and then we have this oscillatory behavior. When we apply this function, this e to the I k mu x mu, to our dispersion relation, this is the dispersion, well, more accurate. When we apply it to this, we get, I keep on calling this dispersion relation, we get something that looks like k mu equals m squared. This here, more accurately, is the dispersion relation. What is this? This tells us this is actually something deep. Along with this oscillatory behavior, we see, or in our solutions, we see that there's a deep connection between the momentum 4 vector and the mass of an object. What does this look like? This looks like K0 minus K1 minus K2 minus K3 equals m squared. More explicitly put, KT minus KX minus KY minus KZ equals m squared. And furthermore, we can write this in terms of vectors and covectors. kt, kx, ky, and kz. kt, kx, ky, kz, like this. This is equal to m squared. And so there's a deep relationship. We're seeing that there's a deep relationship between oscillatory behavior and the mass of an object. And the book mentions this briefly, but this is, to me, this is also something of a philosophical quandary, if you will. Not really a quandary, but an interesting thing that comes out of this oscillatory motion. This idea that the heavier something is, that's directly related to how much it oscillates in space and in time. So we have this interest. This is a dispersion relationship, is what it's called. And so we can take a look at this a little bit more. So we're saying that m squared, I'll just rewrite it, is equal to k mu, right? Well, this is equal to k0, just like I've said, minus k dot k. This is just another way of writing the spatial components out. These are, when we put this little vector on top here, we're saying that this is these are spatial vectors. Okay, and then we can do something interesting here. If we assume that our particle is just moving in one direction, say the z direction, if we assume that, well then we get k0 minus k z squared, because you get kz times kz, and that's just kz squared, and that equals the mass squared. So k0 squared is equal to the mass squared plus kz squared. And so k0 is equal to the square root of m squared plus kz squared. And so therefore, our covector k mu looks like the square root of m squared plus kz squared, 0, 0, and kz. Because again, we're moving in the kz direction. It could be kx. If it was kx, then this would be left. If it's moving in a combination between kz and kx, then this is obviously different. It's obviously a little bit different. And so that is a little bit on this dispersion relationship. We can also consider, if we recall the Lorentz condition, right? The Lorentz condition was that 0 equals d rho a rho, right? So if we recall, this is the Lorentz condition. We have a vector, and this is a gradient on a gradient of a vector. well, this is the same thing as d rho times e rho times f of x rho, right? Where f of x, again, is just some function of x. Where we said that f of x was e to the I k mu, not m, x mu. And this is our e rho. Our derivative becomes a k mu, or a k rho, I, because we're just taking, or when we take the derivative of this, we just bring that over. That's something basic that you get out of calculus. All right, this is 0, this is 0. All right, well, we can divide both sides by this and I to get that 0 is equal to k rho e rho. And so for any field excitation traveling in the z direction, this implies, we can write this out a little bit more explicitly here. I'll rewrite it. 0 equals e rho k rho. This implies, if we're just traveling in the z direction, the x and y components are not restricted in any way. So this means that this is E0 K0 minus E1 K1 minus E2 K2 minus epsilon 3 K3. And so what this again for a field excitation traveling in the z direction, which is this direction, we have a restriction on K3, and we have a restriction here. That restriction again was right here. If we know what Kz is, then we know we can calculate what our temporal component is. But for the x and y, we can set those equal to anything we want. And so what this means is that E1 mu is equal to 1, 0, 0, 0, 1, 0, 0, and E2 is equal to 0, 0, 1, 0. These are the basis vectors for what's called the internal structure of our A vector. Okay, so I might have been a little bit all over the place here. Let's recap a little bit before I move on. We discussed the dispersion relationship. The dispersion relationship is an interesting connection between oscillatory behavior and the mass of an object. And then we said, well, let's remember the Lorentz condition. Let's see what this means for our vector, or our potential for vector A. Well, if we say that the potential for vector has internal structure determined by this epsilon and behaves according to F, this is the space-time structure is what it's called, then what we find is that the internal structure of A has components to it. All right. there's another linearly independent component from these two objects, namely, and we can confirm this to ourselves, call it L. This is what the book calls it. It calls it a linearly independent polarization vector. What these are polarization vectors. Excuse me. They're polarization vectors, and this is going to be kz 0, 0 square root of m squared kz, times, plus kz squared over m, where E L mu and E L mu equals -1. We can confirm this, the book confirms this. If you want me to confirm it, that'll take a little extra time. I know I'm not really that interested in doing it. It's not really that hard. If this is something you want me to go over, then maybe I'll do a Patreon. I'll put a video on Patreon on this. But again, this isn't really that hard to determine. All you have to do really is take this guy and put it in, again here, so we're saying we take this guy and we put it in for, that is for here, right? If we do that, then we'll find out that these have to normalize to -1. Okay. So I'm going to give a picture now on what this might look like. So what this looks like is, here's our field. Here's our field. Again, we're just talking classical fields. Nowhere have I ever actually started talking about quantum fields. I know that's a little frustrating, but that's how this book rolls. Nowhere have I started to talk about quantum fields yet. What we've been doing so far is investigating classical fields, and what the dynamics of these classical fields are. So we have a Klein-Gordon field, have a classical Dirac field, and we've been discussing a classical vector field. Quantum fields are going to come into play when we start considering commutation relationships between a few things. And that is actually going to be in like chapter 9, I think, of this book, if I remember correctly, or something like that, chapter 9 or chapter 10. But still, this is, we're just talking classical right now. We've been just talking classical up for most everything we've been talking about. It isn't until we get past the quantum mechanics primer chapter, which is like chapter 8, I think, where we'll start talking about quantum fields. Anyways, the picture here is that we have at some point our A row. And our A row can be seen as a vector. Here's our A row. So maybe I will redraw this a little bit better. So here we have our A row. This is a little bit of a misnomer because this vector covers space, right? But at every point in space there's a vector. So this picture is a little bit misleading, but it's the best I can do, right? It's the best I can do. So this vector has a tiny little as a tiny little, I'll zoom in on here, coordinate system, if you will. And the basis again, this is the internal structure of the field. E1 E2 EL, and this vector a row lives as a combination between these three linearly independent vectors. And so I'm pushing on 20 minutes. I usually go 30 minutes for these things, but that's really what I wanted to talk about in this video. We really just talking about this dispersion relationship and what this means for the mass, again, what this means in terms of the mass of our field, and what this means in terms of the polarization vectors, what these are called. These are called polarization vectors. And the polarization vectors, again, they emerge out of considering this dispersion relationship, right? So we went from we went from considering dispersion relationship. We went from considering the dispersion relationship to finding out that finding a Lorentz, or from the Lorentz condition, we found, and internal, and considering internal structure, we found out that, or we come to this notion of polarization vectors. So these are all concepts that you'll come across in quantum field theory, even in quantum mechanics. These are all concepts you'll come across, and they're all deeply interconnected with one another. We have this dispersion relationship. When we consider this dispersion relationship under the Lorentz condition and under internal, and given that we are stipulating there's some sort of internal structure here, we get our polarization vectors that emerge out of this. So this is very interesting, and this is something that we're going to want to consider, or just keep in the forefront of our minds as we go forward in this book, because this book, again, when we keep this kind of stuff in mind, it really does help us keep track of what's going on, basically. But yeah, excuse me, but yeah, if these videos are something that you like, if you find this kind of stuff interesting, then please go into my Patreon page, visit my Patreon page, please hit that subscribe button. The more you donate, the more I'll be able to provide videos or educational videos for you on advanced topics in physics. And with that being said, I will see you guys in the next one. Bye.